So we're going to start off again with damped harmonic motion. We dealt with it before, but we only dealt with a single case. In fact, there are 3 distinct mathematical cases for the equations of damped harmonic motion, and we're going to explain all of those now. So the situation, the setup is as follows. As we've seen before, we have some force acting on a spring, a restoring force, and we have some damping. The damping could be due to fluids or the air or whatever it is, just some form of energy loss, but we're assuming that's proportional to the negative of the velocity. And the restoring force, again, is given by Hooke's law. It's proportional to the negative of the displacement. The viscous damping, proportional to the negative of the velocity, as I've said. And so in total then we have sum of the forces, mass times acceleration, is equal to the restoring force due to Hooke's law, and the damping, which is proportional to the velocity. We can rearrange this into a homogeneous differential equation. So we've got a whole bunch of terms here that depend on x and its derivatives, and it's equal to 0. And there are some maths terms that you may have heard elsewhere that we should just mention here to put them all in context. So this damped harmonic motion equation is homogeneous, so that each term of the differential equation has x or one of its derivatives in it, and there's no term that does not depend on x. It's linear. There are no terms that depend non-linearly on x or any of its derivatives, so there's no x squared or anything like that. It's a second order equation, so the highest order derivative is 2. There it is, the second derivative. If there were a triple dot on here, it would be a third order equation, but this is a second order equation. And we're also going to say that if we have 2 solutions, x1 and x2, that are solutions of the linear homogeneous differential equation, then linear combinations of these solutions are also a solution. So if we can find basis solutions, x1 and x2, then linear combinations of x1 and x2 will solve these equations, and these constants, c1 and c2, will allow us to fit initial conditions to this equation, because when we look at the beginning of the motion, it'll have some initial position and some initial velocity that we need to fit. And with 2 derivatives, we need 2 constants that we can fit to our initial conditions. Now, in general, an nth order linear homogeneous equation will have n arbitrary constants in its general solution, and we need each one of these n constants to fit n initial conditions, because a third order equation would need initial positions, initial velocity, and initial acceleration. A fourth order would need the rate of change of acceleration, which is called jerk, by the way. All right, so we'll rewrite this equation of motion. We'll rewrite it like this, where gamma is r divided by m, and omega naught squared is k divided by m. So I just divided the entire equation through by the mass m. The neat thing about writing it like this is now that gamma and omega naught are both frequencies, so they have units of seconds to the -1. So they're angular frequencies, in fact, so radians per second. And we're going to try a solution of this form, e to the alpha t, so an exponential solution. That means that the derivative of our solution, x dot, is alpha e to the alpha t, and the second derivative has an alpha squared out the front. And we can substitute this x and its derivatives back into this equation and see if we can solve it. So if we do that, we find that our equation can be written as alpha squared e to the alpha t, alpha gamma e to the alpha t, and omega naught squared e to the alpha t. We can take out a factor of e to the alpha t, and we can divide through by e to the alpha t, because it, strictly speaking, equals 0 nowhere. And so then we have this quadratic equation here for alpha, and we can solve for alpha. Using the equation for solutions to a quadratic, we find that alpha has 2 possible solutions. Either it's negative gamma on 2 plus square root of gamma on 2 all squared minus omega naught squared, or it is negative gamma on 2 minus the square root of all of that. So the 2 possible roots of this equation. And therefore, we have a general solution to our equation with 2 fitting parameters, c1 and c2, and the general solution is c1, some constant, e to the alpha 1 times t, plus c2 times e to the alpha 2 times t. And this will be a solution to our equation. And now there are some different regimes that we can consider for what alpha is going to be, because alpha may be a real number, alpha may be a complex number, and that will determine what kind of solution we have to this equation. So this is our equation and this is the solution. There are three possible cases. The first case is that gamma on 2 is greater than omega naught. And inside the square root here, what that means is that under the square root, we have a positive number, which means the square root will be real, and it'll be the square root will be a number that is less than gamma on 2, which means that alpha 1 and alpha 2 will both be negative numbers. And so this system is then called overdamped. There is no oscillation in this case where gamma on 2 is greater than omega naught. It's just exponential damping. The second case, and this is the one that we dealt with earlier, is the underdamped solution. In this case, gamma on 2 is less than omega naught, which means that underneath this square root, we have a negative number, which means that the square root will generate an imaginary number. When this imaginary number pops up into this exponential here, we end up with a e to the I omega t term, and that gives us oscillations. But we also have damping, which means we have a damped oscillatory solution. The third case is kind of the pathological case, and that is when gamma on 2 is exactly equal to omega naught, which means that alpha 1 and alpha 2 are equal. In this case, is called critically damped. And in fact, in this case, we're missing a solution, because if alpha 1 and alpha 2 are equal, we only have one solution to the differential equation. We need to find a second one. So we'll deal with that case when we come to it and discover that we actually need to add a solution to deal with only this crazy pathological case.